Just in case you guys were wondering, these slides are posted, so you don't have to take photos of the slides, just for future reference. It's easier that way. OK, so I'll get started. Thank you all for coming. I'm Ilan Filonenko, and I'm a software engineer at Bloomberg, working on the data science infrastructure team. And today I'll be talking about scaling and securing Spark on Kubernetes at Bloomberg. So I'll begin by talking about data science at Bloomberg. Then I'll discuss the part that Spark plays in the ETL pipelines that we have, and how we work to secure and scale it with disaggregated compute, and then some future work that lays ahead. So machine learning workloads come in many shapes and sizes, but the challenges that ML teams face are quite common, even in established enterprises. Some of these concerns include data permissioning, scheduling, and resource monitoring for tasks that include feature generation, model training, and model development. In an effort to solve some of these challenges, specifically regarding ML questions and problems, Bloomberg has developed a versatile data science platform that provides a sophisticated compute environment for engineers to manage their ETL pipelines and their model development life cycles. To do this, the solution presents a variety of ETL and training jobs that run through various runtimes, an identity management solution that makes security a first-class citizen, resource governance for teams in forms of shared workspaces, and inference solutions that are designed with Lambdas using Knative for building, serving, and monitoring models. One integral component of most ETL pipelines is Apache Spark. So just as a show of reference, how many people know of Apache Spark in this room? OK, awesome. That's really great. And how many of you actually use it within your Kubernetes environments? OK, even better. Now we're going to discuss that a little bit. So just for those who didn't raise their hand, Spark functions as a robust framework that uses a general execution engine to provide distributed data processing. And one of Spark's powerful applications is feature transformation and generation, in essence, converting large unstructured data into something more structured. And Spark runs as independent processes on a cluster coordinated by the Spark context over here that's running in your driver program. The Spark context then can connect to several types of cluster managers, which include Standalone, Mesos, Yarn, or Kubernetes. And these cluster managers, in essence, just allocate resources across applications. Now, upon receiving provision executors, Spark then sends your application code to the executors, and then after which the Spark context would then send tasks to the executors to run. The executor would then use a variety of caching strategies for various Spark files that are traditionally stored on the local file system. So that would be, for example, that's displayed over here. And persistence is also traditionally done to local HDFS data nodes for stuff like Hive tables, which is stored over here. At the same time, executors might need to communicate with each other in order to read from their other local caches. Now, storage relating to the data that you wish to process is also traditionally colocated for data locality speedups. As such, you can see how the storage and compute are on the same node, thereby colocated. However, this design is constraining when we try to extend Kubernetes as a cluster manager for Spark, which we will elaborate on later, but also it isn't consistent with the industry's trend towards promoting disaggregated compute. But what is disaggregated compute, or disag? So disag is the cluster separation of storage and compute. And as Bloomberg's technical problems grow in scope, so does our data. And unsurprisingly, compute nodes that aren't designed for large disk space can't handle certain workloads if Spark is doing its file caching by writing to its local file system. And unsurprisingly, compute nodes that aren't designed in this way will now be starting taking advantage of the hardware that you can now specialize. So for example, your compute nodes will now be RAM heavy, while your storage nodes can be disk heavy. Disaggregated compute will also allow your cluster management and hardware upgrade cycles to be done separately, especially within Bloomberg, where we have specialized teams that manage storage. This is particularly appealing. Disag will also allow you to persist your storage nodes while your compute nodes can be brought up elastically. And this is especially useful in cloud environments where you can scale up and down EC2 instances. So Bloomberg has incorporated this disag approach in the design of its data science platform. And what you can immediately notice is the separation between storage and compute. Our users store their data in S3, HDFS, or some other data stores of their choosing. And one goal in building this platform was to make it easy to access data in various data sources. So on the bottom right, we have our compute cluster, which is made up of many CPU and GPU nodes, which has all of its resource scheduling and management done via Kubernetes. A user then submits a platform job to this compute cluster, We provide various pieces of tooling and ML facilities around the compute cluster for our users. And some of this tooling includes a custom job CLI and a job history UI. Now let's dig into the internals of the job, the platform job. So the lifecycle looks something like this, which is traditional for like an operator controller architecture. So user submits an API resource to the Kubernetes API server in a declarative format like YAML. Then there's a platform controller, which watches for changes to a resource of interest. It's worth to note that this controller runs in a privileged namespace. The controller then acts like a state machine by reading the updates that happen in an appropriate way by looking at the current state compared to the desired state of the world. Now, because the controller runs in a privileged namespace, it can now submit relevant changes and requests back to the API server. So this could come in the form of a pod resource, for example. The API server will then schedule the pods appropriately. And as such, the Spark job can now be thought also as a platform job. Thereby, the controller is responsible for requesting resources needed to spin up a Spark cluster. Now, you guys probably seen this diagram a lot of times, but let's talk a little bit about how this kind of fits into the Kubernetes world. So in the initial days of the data science platform, we decided to launch Spark via Standalone, which means that the driver communicates with a master pod as opposed to the Kubernetes API server directly. As such, by using an init container, the driver would wait until the master and worker nodes are provisioned and reachable before launching the Spark application defined in the job spec. It is worth to note that our storage nodes are actually separated, which contain most of the user application data from the compute cluster. However, the cache layer, as you can see here, is still sitting on our compute nodes. Now, some drawbacks become very apparent, the first of which is that you're unable to elastically scale within a Spark application, as there's no direct communication with the API server. The second was that the master node and worker nodes needed to be set up before launching the Spark application. So if you guys use a lot of Jupyter, this is particularly problematic when you're trying to create a Spark context within Jupyter, as it would be required that you pre-launch a headless Spark job that you need to interact with. Now this, traditionally, as we were scaling up our user count, we found that this led to a lot of problems with resource management, as sometimes these clusters weren't properly reaped upon notebook termination. So to explain that better, pretty much users who would launch a Spark job within their Jupyter notebook would need to be responsible to terminate that same Spark job, and as you can imagine, that's not always the case. So to solve this, Bloomberg actively worked to introduce Kubernetes native integration into Spark 2.3 and 2.4 to solve these very issues. Now we can see the architecture slightly change by having the driver directly communicate with the API server. So as such, you can now think of the driver as a controller in the architecture of the data science platform. So this is the current state of where the community is at in terms of Spark and Kubernetes. However, there were issues when we started integrating this within our production Bloomberg environment. So now I'm going to identify some of these issues and how we worked with the community to solve them. So because of the security restrictions imposed by our cluster administrators, due to the sensitivity and regulations of the space that we worked in, users are unable to launch pods from their own namespaces. So instead, users need to interact with pods that are launched by a controller that is running in an admin namespace. Now this use case might be one that is employed in your environments as well. Therefore, to have a driver function as a controller is not possible within our environment because it's creating pods. Secondly, the vast array of data sources that Bloomberg uses are all secured, and the process of data retrieval within our compute jobs lacked a managed identity service that integrates with Bloomberg jobs, especially with Spark. And lastly, Spark's caching on local disk makes enable a fully disaggregated Spark environment impossible. So just go back a tiny bit. This caching that's handling here, because it's being routed to the local file system, restricts us from doing a fully disaggregated environment. So let's start with security. As was said earlier, the ability for pods to be created from a user's namespace is forbidden. But even if it were allowed via some form of restricted webhooks, these webhooks would be applied to all pods, including system pods, which could bring a noticeable slowdown. Furthermore, there's no ability to do an all or nothing pod creation, where like all pods required for a Spark cluster would wait to be registered with the API server until the resource quota is available. This use case is important for different resource scheduling scenarios where you would wish to tune when to create a batch of executors based on the cluster load. So this customization would solve some complications that could arise with regards to resource deadlocks between competing Spark jobs on a single workspace. So Bloomberg developed a solution by extending an API that we developed that hooks into the Kubernetes cluster scheduler backend. And this API this API's default implementation extends the current logic, which would just launch pods. But internally, we extend this API to create and update a custom resource that we call the exec pod scaler. But users for this API, if the community wants to use it, can extend any form of custom resource that they choose. So let's jump into an example Spark job and to see how we leverage the exec pod scaler custom resource definition. So the user who lives in the user's namespace, he would begin by submitting a Spark job to the API server using some declarative format like YAML, for example. A controller living in a privileged namespace would watch for custom resources, and upon seeing a request for a Spark job, would provision a driver pod with all the appropriate webhook and modifications, and upon there being enough resources in the user's quota for the driver and the executors, the controller would then launch a driver pod. Now, by measuring the quota needed for the driver and executors, this allows for us to avoid hanging drivers who are deadlocked from launching executors when competing Spark jobs are all running in the same instance, which is pretty important, because there's a lot of situations where you might have a heavy cluster load and drivers that are just waiting, so you now have the overpopulation of too many drivers. The driver pod will now run the Spark application, and upon it requesting executors in its backend, it would create an exec pod scaler custom resource, which the controller will also be watching for. Upon seeing a request for an exec pod scaler custom resource, the controller will then provision the executors with the appropriate webhooks and modifications, upon seeing, again, the appropriate resource quota being available for the requested executors. This is to handle the race condition in which multiple Spark jobs could have been started after the period in which the driver plus executor resource count was available. To note, all executors are created at once upon the availability of resources, as opposed to having only a portion of the executors created and subsequently blocking simultaneous Spark jobs who might be in the same deadlock scenario. So as you can see now, the driver does not create the executors, which would then give the ability for users to customize their own pods. But instead, the driver will instead be watching the executor pods that are to be created, and by filtering on unique Spark application pods, the driver will then send the Spark application information, such as the application specs and tasks, to the executors. So after solving one of the challenges with compute security, another one that was presented was with relation to storage security. Bloomberg has a variety of data sources that it uses for its model development, each of which are highly secured. And to simplify the experience of using the data science platform, when interacting with, for example, Kerberos HDFS or S3, the data science platform designed to manage token service for all jobs. The token service is serviceable via the simple inclusion of a user identity name that is specified in your job specification. And one of the features is that it automatically handles Hadoop token renewal and retrieval for HDFS, Hive, HBase, and the like. Now, by putting the token service behind the controller, this allows for reusability and standardization across a variety of jobs, including Spark, and also another popular job that uses HDFS data, which is TensorFlow. So let's see how it works. So the controller from an admin namespace communicates out to a variety of data sources and management tools, which in Spark's case includes HDFS and S3. The user begins by creating an identity custom resource, and the controller will then read the custom resource and have the user's privileged credentials stored as a secret for jobs in the user's namespace to access. When a job is looking for a particular identity, the controller will then handle bootstrapping the job with that identity resource and automatically handles updating expiring tokens when dealing with long-running jobs. Now, these long-running jobs are quite common in Bloomberg's ecosystem, as I'm sure it is in yours, when we deal with Spark ML as well as Spark streaming jobs that could run for weeks. So how will that update look in the world of secure HDFS? Well, the controller will then function as a proxy user on behalf of the job user. And using the controller's own principal, it would receive an HDFS service ticket by communicating with the Kerberos node. Next, it will use that ticket to receive a delegation token that's bounded to the job user's principal to ensure that the job user only has access to the job user data. And we also provide additional security by putting the token in the secret only privy to that user. Therefore, the expired token would be updated in the secret. The driver and executors, based on Kubernetes, will automatically detect updates to the secrets and have their tokens renewed as a result. However, despite detecting updates to the token file to hook into Spark, we added an additional feature to Spark Hadoop utils that allows for the driver, upon changes to the token secret, to send token updates to the executors to then kick off the same UGI process that is consistent across all resource managers. So in addition, we saw that in other jobs like TensorFlow, which lacked this Hadoop util UGI feature, we needed to support renewal to be done via delegation tokens. And so we proposed a patch to Hadoop core to support this. So the reasoning for this is the following. The implicit The implicit assumption in the old implementation was that yarn functions as a scheduling agent with access to appropriate key tabs for the renewal of Kerberos tickets and delegation tokens. However, jobs that would interact with Kerberos Hadoop services like HDFS, Hive, or HBase and use an external scheduler like Kubernetes typically don't have access to the key tabs. So in these specific cases, delegation tokens are a logical choice for interacting with a Kerberos cluster, as tokens could be issued based on some form of external auth mechanism like kubeldep, for example. So solving the first two challenges we listed, the last one we wanted to discuss was scaling Spark by enabling disaggregated compute in a traditionally collocated application. So let's go a little into the Spark internals to allow for us to understand where the restrictions exist, stopping us from enabling disag. So let's define an example user story. So you have your example Spark application. So let's say you have a large data set, a few petabytes in size, for example, and you wish to run a couple simple transformations on it, like adding +1 to your values, and a few more complex operations like sort, for example, before collecting the results into the driver. So Spark leverages an operator graph for users to allow for them to apply a variety of transformations that won't get sent to the DAG scheduler until an action like collect, for example, is performed. So in this diagram, we show how operations are broken up into stages, which stage can contain tasks, these tasks based on data partitions. Now, so there could be many tasks pipelined together in a single stage, and in the end, the stages are passed into the task scheduler, which I said earlier is responsible for distributing the tasks to executors. So if you pay attention to the space in between stage n and n+1, you can see an all-to-all communication that is called a shuffle operation. So this all-to-all communication is critical for operations like sorting, which is done by your example Spark application above, as I said earlier in the user story. So in technical terms, shuffle is when you move data from one stage to another while partitioning your data so the reducers receive their respective partitions. So there are two specific important things to note about the following shuffle example I illustrated. The first of which is that Spark implements shuffle using files on disk. Now, this was designed with strong fault tolerance guarantees, as well as the simple reasoning that not all shuffle data could necessarily fit in memory, which, as you can imagine in the use case I just gave with petabytes in size, is quite common. The second is that in stage n, we have 4 mappers for the 4 partitions, and in stage n+1, we have 3 reducers for the 3 resulting partitions. So this serves as a valuable introduction to a concept called Dynamic Resource Allocation, which is when you have a Spark application giving back resources to the cluster if they no longer need those resources. And they can also request them back again later when they need it based on their demands. As you can see, we could actually give back a worker resource after completing stage n as we move to stage n+1. This is valuable as executors that aren't given tasks should be repurposed for other Spark jobs. So in the case that we want to rescale our executor count, we need to ensure that these shuffle files aren't lost when executors are scaled down, and that these shuffle files are available for newly created executors. Now, what kind of files are used by Spark to enable shuffle? The first kind of temporary file that Spark uses are spill files. These files are created when a task running on an executor spills to disk after being unable to store it in memory. And as you can imagine, this can happen quite often as many spill files can be created on a given stage. The next kind of file that can be created is a shuffle file, which, as I said earlier, are created whenever you want to do a shuffle operation between stages. This file is created by the mapper via shuffle write, which the reducer would then read via shuffle fetch, but only parts of partitions. And in the case that spill files do exist, the mapper will then merge all the spill files that happen in the map stage and put that merged content into the shuffle file for later stages to then have. So in the current implementation of shuffle, shuffle files involve 2 files when it comes to shuffle fetches by later stages. The first of which are the data files, which are written by the mapper, and the second is an index file, which appropriately indexes where in the data file the partition begins and ends. So for reading shuffle bytes, you would first read the index file and determine where in the data file you then seek and read. So as you can imagine, in the case of a large index file, this could have long seek times just for retrieving indexes. And obviously, in the case of large data files, this would have a magnitudes larger seek time. Now, remember when we discussed dynamic resource allocation, where you don't necessarily need 4 executors if you only have 3 partitions? Well, this scaling of your executors is crucial for scaling any production Spark environment, and is critical at Bloomberg specifically. So the way that the external shuffle service enables dynamic resource allocation is that instead of directly communicating with executors for their shuffle files via RPC, you could, which could be potentially scaled down, for example, in the case of a dynamic environment, you would then talk to a shuffle service instance instead. Now, in a traditional Spark on Yarn environment, this shuffle service instance would live on every node and function as a file server for reading data files, as well as a cache server for index files. And as executors, upon finishing its shuffle write, they would register those written blocks with the shuffle service. And later, the shuffle fetches are enabled by the shuffle service by streaming data from the node's local disk to the appropriate executors. Now, there are numerous problems with this that we soon found. The first of which is that there's a lack of resource isolation. So if the shuffle service uses too much memory on the node, the whole node goes down and then takes on all the executors that are running on that given node. There's also a lack of replication in shuffle service instances. So without multiple shuffle service instances per node, you'd have a case where a collocated shuffle instance fails, for example, and this will require replaying of the entire DAG for the executors on that node so that the shuffle files can be recreated. However, they're all sitting on local disk anyway, so there's no reason for you to recreate them. Furthermore, the continuous uptime of the shuffle service is required for the node to then accept executors to run. So if a shuffle service goes down on that node, then no executors can be schedulable on that node. And lastly, what happens when we move this to Kubernetes, for example? So in Kubernetes world, there would be an assumption that the container volume would be shared between the executor and the shuffle service. Now, this design breaks in certain cluster configurations where collocated storage is not allowed, which I assume is pretty consistent across this room. As such, there needed to be a solution where we could redesign the communication between Spark and the external shuffle service to thusly enable dynamic resource allocation. So the solution Bloomberg developed with Palantir, along many developers from many companies, would be an API within the current shuffle implementation that allows for pluggable writing and reading of shuffle bytes. So this API allows for developers to extend their shuffle storage with any preferred backing storage layer, as well as a database layer that they can plug in, thereby promoting disaggregated compute for shuffle files specifically. The API leverages a plugin tree that defines various components in enabling shuffle. The driver components allow for application initialization and cleaning. The executor components provide flexibility towards writing strategy, may it be output streams or writable byte channels for Java Neo optimizations like file channel or socket channel, and flexibility for reading as well via the shuffle readers. And the shuffle locations allow developers the flexibility to create unique solutions that can be comprised of primary and backup locations. So where does it become powerful? So given the problems that we addressed a little bit earlier, we developed some solutions. So both Bloomberg and Palantir have been actively working on various example implementations. I'm going to go through some of them, as there could be a use case where it becomes very helpful for you guys, and I would love to hear your comments on them. The first of which is using individual file servers. So in essence, you're treating the shuffle services as file servers that accept streams of bytes as input for writing shuffle data, and providing endpoints for reading files as byte streams. The way this will work is that the executor would begin by writing its shuffle blocks to an external shuffle service instance that will function as a file server for its own files, for its own file system, which is in the case over here. The executor can then optionally handle replication by doing a secondary write to another file server, for example, the one over here. And what's unique about that one, for the sake of example, is that instead of writing its block to its local file storage, it's writing to an external file system like HDFS. Upon completion of its writing, the executor would then report the backup, would then report all of its primary and backup and secondary locations to the driver. Now, something to note in this specific design is that there are two network transfers if the file server is communicating with an external file system. The first network transfer will then happen with actually communicating with the file server itself, and the second one will be communicating with HDFS. However, there are some clear advantages to this design that cover the problems that were addressed. Every external shuffle service instance can be run on its own host or in an isolated container. So if any external shuffle service instance fails, only the container running the shuffle service will be affected. So therefore, it's not necessary, but in its implementation, you would not need to collocate your shuffle services with your Spark executors, which is important because the whole point is that we're trying to separate the two. So as the number of executors grow in the system, you're also able to independently scale your shuffle service instances. Obviously, once you put the shuffle service instances behind a proxy, you then have another network hop you have to do, but that's if you want to do that. The external shuffle service does also not need to share local storage with the executors, and in fact, the shuffle services themselves could be completely stateless if they communicate with an external storage like they do in the Red 4. And in the case of persisting to an external storage, the shuffle service instance can be shut down as well, and the underlying data can be serviced by any remaining external shuffle service instances. In another example, in this design, we were trying to asynchronously back up our locations as we were writing our shuffle blocks to local disk. So upon writing our shuffle blocks index files to the executor's local file system, the executor would then asynchronously back up its shuffle blocks and index files to a stable DFS. Now, because it is async, the executor can immediately report to the driver the primary and backup locations upon finishing its local write. However, what happens when we do the read from the backup and it's not done writing, which is quite common probably? One strategy is to do an asynchronous shuffle fetch, such that you would open up concurrent input streams across all your file locations, both primary and backups, and take the fastest response. And otherwise, you would just block if there's no response. So the solution is also satisfying for the problems that we listed. Since we removed the external shuffle service here, if one executor fails, it would only impact the application that executor is a part of. Also, the backup storage layer would be quite resilient and highly available. And the solution is compatible with containerized storage since the local disk does not need to be shared between any two processes in the system. Exchanging shuffle data would be done either via RPC between executors or between RPC between an executor and the remote file servers. Sorry, between the remote backup storage. So the last implementation that's an example is to do a direct write to distributed file system or some kind of stable DFS. So where the driver would maintain all of its own shuffle metadata without using a shuffle service. And the executor could then circumvent the need for a file system and would directly write its shuffle blocks index files to the stable DFS. So something to note here, in contrast to the individual file server example that was earlier, you now only require one network transfer as you directly communicate with the DFS. And for further optimizations, you could also leverage an in-memory key value store like Ignite or Redis, and you could actually remove the need for index file completely by just having the partition be part of that key. This example also solves the problems they were addressing earlier because it provides the necessary resource isolation, also with the scalability factor, that the scalability factor only relies on the scalability of the shuffle operation as well as the scalability of the data storage system, which in this case is going to be quite performant. So upon completion of our proposed API, and despite making some headway on trying to run some of our Spark deployments use these implementations, there's still a lot of work that needs to be done, obviously. So the API and some of the implementations I present here are formalized in an SPIP under the Jira ticket Spark 25299 and is an active discussion via the Spark dev mailing list. So many different shuffle implementations, specifically with remote pluggable shuffle, are presented at various conferences, and the main focus of this work is to try to unify these implementations with this form of a generic API. However, in the work of enabling a fully disaggregated Spark environment, there are still challenges that remain. So the work that still needs to be done involves fetch failed exception handling in the DAG scheduler for failed shuffle fetches, which is quite common. So these fetch failures are primary sources of query latency in Spark, and as such, we would like the implementer to customize the exception that is thrown for their given specific implementations. So for example, in the case of your direct writing to DFS, you're going to have a situation where you don't want to necessarily do a fetch failure because you want to do generic exception because the chances of you being unable to fetch from DFS is quite low because of the scalability of your backing store. The next thing we have to do is extend the API to handle spills and cache files. So cache files is another kind of temporary file that I didn't get into in this talk. Luckily, these two APIs are quite orthogonal to our work. And so we still need to necessarily extend them to make this fully supported. But luckily, we'll also pretty much those are the last two things that are needed to fully move that caching layer outside of our compute nodes to then fully promote disag. And the last thing is to do performance benchmarking across different implementations before deciding which one is appropriate for Spark's environment. As always, we encourage collaboration as we move towards disaggregated compute. As we move towards disaggregated compute, and I am excited to see where this work will go and how we can work together. Thank you. Okay. Yeah, any questions? Awesome.
Hello.
Oh, it works.
Thanks for the presentation. I've got one question. Maybe you know why all the old work from Spark on Kubernetes branch was removed in Spark 2.4, because there was official Spark on Kubernetes project, and there was dynamic resource allocation there and external shuffle.
Okay, so the question was the removal of the fork. So I was part of the team that made the fork. And so as we're moving upstream, there need to be certain considerations that were required for us to move upstream, and that was to be consistent across the cluster schedulers. And our approach was very specific for containerized environments. For example, we removed the init container from a lot of our logic for the driver, which included some of the work that was necessary for, I believe we also had a file server that you can actually write most of your files if you wanted to do local file reads. And so a lot of that was in pretty much you're using too many Kubernetes-specific things in an environment that's supposed to be agnostic to cluster managers. So there was just a back and forth between the community where we needed to redesign it. And as I discussed earlier, the new design of the generic API promotes the ability for us to have various different shuffle limitations. Just leverage these wrappers that allow for you to directly call write output stream, read output stream, and various shuffle locations that could be any location. OK, wait, maybe we should keep this in the center. OK.
Thanks. You mentioned that you have a quota allocation for the spawning of executors. Could you talk a bit more about that, how you manage that quota?
To do what, sorry?
For the users to spawn executors. So this quota management, resource quota management, how do you do it?
So you pretty much define a resource quota per your namespace. So our workspaces are defined around a namespace, and then based on that, you just calculate the size of your cluster that you're specifying. Like let's say when you launch your Spark job, you request executor memory and driver memory. Just based on that calculation, you would then determine if the job is too large. And the question of how you would handle scheduling, like gang scheduling or FIFO or whatever of that nature between Spark jobs, that's still under investigation, whether there's an appropriate place for that in terms of how you schedule jobs in terms of resource scheduling. But the simplest approach would then be just like whether you're pretty much you're giving too many resources to your Spark job to then be blocked from launching, if that makes sense.
Thanks.
I think there was another question.
Hello. Okay. We are currently running Spark on Yarn, but most of the reason is because we have a pool of resource which is purely just for Spark, and we have many researchers running Spark job on it. For Yarn, they have this ability to preempt jobs. So when the cluster is empty, we allow one researcher to just fully use the whole cluster. But when the second researcher joins in, Yarn will make sure it split this cluster half and half to make it fair for the two researchers. But on Kubernetes, it doesn't look like we can do this. And is it the feature you're going to support in the future?
So fairness scheduling?
Yeah.
Is that internal to Spark, or are you talking about to Kubernetes specifically?
Well, it's on Kubernetes. So we want to use Spark on Kubernetes. But for this reason, we have to run it on Yarn.
I think that could be promoted. Fairness scheduling should be able to be done logically, but it's not a Spark internal thing, so I guess it's based on the cluster manager itself. I would say, I'll take that offline. I'll have to look into that a little bit. Thank you so much. Oh, we have one question in the back. Yes, so this is the slide over here. So this work is already written up for Spark 25299. And so we already submitted an SPIP for that. And right now it's in discussion, and then we're going to start a voting soon. And then it's a matter of whether we can get into Spark 3.0 or Spark 3.1. But yes, the whole function of this is that it's going to be an upstream work. And then the implementations would probably be surfaced as this fork, so that you can, for example, leverage our implementations of the individual file server or Palantir's implementations of the direct DFS writing or whatnot. Any other questions? OK, we got one in the back. Go for it. Can you pass the mic, please?
My question is about performance. Currently, the Shuffle service is a file server that writes the local file system, and it's one of the biggest issue for Spark jobs performance. So when you move to writing directly to HDFS or an external HDFS cluster, have you use it on big workloads, on big Spark jobs?
So the question, I guess, comes down to like query latency in general. Like when you have, how long does it usually take? Most of the time that's spent on Shuffle ends up becoming an issue with regards to fetch failed exceptions. So your fetch failed exceptions are going to cause a predominantly large portion of variability in your Spark job times. And so to stabilize at least that by ensuring that you're writing to a stable DFS, that should at least provide users consistency in their Spark jobs, as well as the ability for it to be faster. We also see that network itself is becoming more and more developed in general. So we're saying that our network costs are going to go down, while determining our disk throughputs. We're seeing that we're focusing more on network than disk throughput. And so we're seeing that when it comes to larger jobs, we want to focus more on not relying on disk throughput, as that's not. You'd say the industry is not moving more towards that as opposed to network. The other thing is that there's some jobs that physically you can't. So there were some other talks by Facebook during Spark Summit where they were discussing write amplification due to shuffles. And so in some cases, for example, 1 petabyte of shuffle operation can result in 3 times that, so 3 petabytes of shuffle files and spill files written, right? So that physically, the ability for you to write that all on disk is sometimes impossible. And so there is a need then to write to DFS, if that answers your question. So it's a combination of there's no way to do it for large jobs, as well as the industry is moving more towards making network faster, because disk throughput is not getting better, in essence. Okay, going once, twice. Okay, awesome. Thank you guys so much. Appreciate it.